Okay, let's try to finish up today's missed lecture. So, this is part 2. Remember one of the things that we found in part 1 of this lecture was a relationship between the potential and the electric field. And we found that the direction of the electric field always points in the direction of decreasing potential. So for this point charge, you see that the electric field radiating out away from it because it's positive. The arrows also point in the direction of decreasing potential. If we moved in towards the charge, we would be moving in the direction of increasing potential. Remember that the idea of potential is to basically eliminate the charge from the relationship when we talk about the change in potential energy. So it's talking just about what happens or what changes occur if we move from one point in the electric field to another point in the electric field. So, but then we can sort of turn it back around and then think about, okay, well, what if I put a charge at this location and then I move it to the second location? What kinds of things change? The charge will move through a potential difference because it'll go from a point of one potential to a different potential. But as it does so, it also undergoes a change in potential energy. Remembering that the change in potential was defined as the change in potential energy divided by the charge, we can just rearrange this and see that if we take a charge through some change in potential, the change in potential energy of that charge is equal to the charge times the potential difference. So this is the potential difference right here, because we're saying, what if I went from a location in the electric field where the potential was V sub B, and then I moved to a new location where the potential was V sub A. So keep in mind that in this case A is my final destination. If the charge moves through that potential difference, it'll undergo a change in potential energy equal to the potential energy at A minus the potential energy at B. So you see, that's sort of what what we see is that when charges move through potential differences, they undergo a change in potential energy. So usually the change in potential is defined in units that we call volts, and then the charge is measured in units that we call coulombs, which we're familiar with. And if you multiply coulombs times volts, the units that you get for energy, as you expect, would be called joules. There's actually another unit of energy that we use when we're talking about changes in potential simply because it's kind of convenient, and that unit of energy is called an electron volt. And basically it originates with this relationship between change in potential energy and change in potential. And so the idea is, what is an electron volt? Is basically when instead of measuring the charge in units of coulombs, we measure it as just the magnitude of an electron. So one charge of an electron, so that if we take something with the charge equal to that of the electron and go through a potential difference of 1 volt, the change of its energy would be 1 electron volt. The conversion factor between electron volts and joules, you can see, comes from the unit for coulombs, or the measurement of coulombs. It's 1.6 times 10 to the minus 19 joules. And so it looks like some of my subscripts and superscripts aren't working. 1 electron volt is 1.6 times 10 to the minus 19 joules. So you may see sometimes things expressed in terms of electron volts, and that's just what they're talking about. It's sort of a shorthand. Oops. So now we're going to go back to these conductors and talk about what is the potential for the conductor. So we already learned in the previous chapter that inside a conductor the electric field is zero. So here we have a conductor. It has some charge on it. Of course, the charge is all on the surface, which we learned is where it would have to be if the conductor was in electrostatic equilibrium. And so because there's no charge inside, there's also no electric field. Once we get outside of the sphere, the electric field actually looks like that of a point charge if the total charge was located at the very middle of the sphere. So it's 1 over 4 pi epsilon naught q over r squared, which can also be written as kq over r squared. So what does the potential in that case look like? So we want to remember that there's a relationship between the change in potential and the electric field. And so if we think about inside the conductor, if we move from, between 2 points inside the conductor, so if I go from point A to point B, we know that the electric field everywhere in the conductor is zero. So the change in potential as I go between those 2 points from A to B is going to have to be zero. If the change in potential is zero, that means the potential has to be constant. So basically, because of the nature of the electric field inside the conductor, if we think about the potential just has to be some constant value. And then as we go outside of the conductor, the potential again will look like the potential due to a point charge. Again, I can write this also as kq over r. That you might recognize that expression from earlier. The potential inside, because it's constant and we can't have a discontinuity at the surface, has to also be equal to this value as well. And so the potential inside the conductor is the same as it is on the surface, which is the potential equal to the potential of a point charge that would be located, again, at the very center of the conductor. One of the nice relationships or helpful relationships that we learn when we're talking about change in potential is, what about the change in potential as I move in a uniform electric field? An example of this would be the electric field between 2 oppositely charged parallel plates. The electric field inside here is constant. And so let's say that I move from one point to another inside of here, if I'm looking for the change in potential. And also the movement is only going to count if it's parallel to the electric field. So first, the dot product is just the product of the electric field and ds. And then I can take the electric field out of the integral because the electric field is constant. And so this ends up to be E times delta S. That's my change in potential. The negative sign is only because of the way that the electric field points in the direction of decreasing potential, and so that's what the negative sign means. So the E field points towards the decreasing potential. But in general, if we're just thinking about the potential difference and we know that it's going to be bigger here and potential is decreasing as I move in this direction, we can use the sort of handy relationship that we see up here, that the potential difference between 2 points separated by a distance y could just be given as E times y. And so this is something handy to remember, that when you have a constant electric field, the change in potential between 2 points is just the distance between the 2 points times the electric field. Again, we're just going to look at some equipotential surfaces. We already found out in the previous video that the electric field lines and equipotential surfaces are perpendicular to each other. So for a point charge where the electric field is radial, then the equipotential surfaces actually are concentric circles here. So everywhere on these circles, if you go around the circle, the potential would be the same. What does that mean? It means, for instance, if a charge moves somewhere on this circle to some other location on the circle, it actually doesn't take any work for that to happen because the charge doesn't move through any potential difference. And so here, as it says, the blue lines are the equipotential surfaces and the red lines are the electric field. Here are just some arrangements of electric field lines and their equipotentials. You probably remember doing things similar to this in the lab last week. Sorry that we didn't get through this before the lab, but now it might sort of click together, because you did do something like this dipole. These are two are the same charge, and you see the equipotential surfaces for that. And then also just some extra things. Now we know that in addition to the things that we know about the electric field of the conductor, remember the electric field was perpendicular to the surface of a conductor, well then that means that the surface actually then defines the equipotential. So the surface of a conductor where the charges are at rest is actually an equipotential surface. And our last thing that we're going to look at is a relationship between the electric field and the potential. So again, we're going to start with this relationship. And so, first of all, we're going to assume, for simplicity, that electric field is in the x direction. And so then our ds is just going to be dx, just to be simple. So here I have delta v then is equal to minus ex dx. And if I take away my integral sign, then instead of delta v, this is dv, and this is equal to minus ex dx. So ex, we can just rearrange this, can be found by taking the derivative of the potential with respect to x, and it's the negative of that. So if we know an expression for the potential, in a sense, it's saying that we can actually then use that expression for the potential to figure out what the electric field looks like. Now, I did it for the simple case of the electric field only depending on only going in one direction and only depending on one variable. It does get a little bit more complicated if you have x, y, and z, because instead of taking the derivative, you take the partial derivative, which you might remember we did when we were looking at waves. So you just take a look at that. If we have more than one component for our electric field, we are taking, to find each of those components, we're taking what we call the partial derivative. Remember, the partial derivative is really not that bad. It's just taking the derivative with respect to whatever variable you're interested in, and then you pretend all the other variables are constants. And so the electric field ends up looking like this. It says that you can write it as also what we call the gradient, because the total electric field, which would be Ex, an xy, and a z component, would be equal to minus dv dx. x direction, minus dv dy in the j direction, and minus dv dz in the z direction. And this is just, the gradient is an operator that looks like this. This is kind of past what you might have done in math, but just sort of as a bonus piece of information. So that finishes up things for today. Hopefully this helps us and we can somewhat stay on track when we return back together for class on Thursday.